Hey, it's Mr. Saltano. This video is going to be explaining equilibrium and Le Chatelier's principle. So first we have to talk about a reversible reaction. So up to this point we've been talking about reactions, and we've been saying that pretty much the reactants react with each other and we have an arrow to the right and then they form the products, right? Well, realistically, many reactions are actually reversible. So for example, rechargeable batteries are a reversible reaction. And what that means is that in addition to A and B reacting with each other to form C and D, so this right arrow, it's also quite possible in many reactions that C plus D would react with each other to go back and form A plus B, go back to the original reactants essentially. And we symbolize this with a double arrow to show that it's possible for the reaction to go both ways. We've seen an example of this before where we have copper 2 sulfate pentahydrate, so that's the blue crystals. And if we heat that, then we end up having this dried out form. All the water has been heated out where you just have copper sulfate, copper 2 sulfate. And then if we were to add water back in, we could go back to these crystals again. So here's what that looks like. So first we have our blue crystals and we're heating it. And it's forming the other chemical. And then we can go backwards if we add water. And we can form the reactants again. And we can go back and forth essentially, because this is a reversible reaction. And notice that we have the double arrow here to sort of indicate that this is reversible. So then, if that's a reversible reaction, then what is equilibrium? So let's take a look at what exactly equilibrium means. We're starting off with 40 reactants. These green particles are reactants. The reaction is a simple reaction of reactants are A, products are B. And our arrows down here are going to show how many particles actually transferred. So whatever number is right here will show how many reactants went to products. And whatever number is right here will show how many products went to reactants. So we're going to say half of our reactants change each time and a quarter of our products go back each time. So let's see what happens. So whenever you have a reversible reaction, usually you only have reactants to begin with, right? So first the reactants have to react with each other to form some products. So let's let that happen first. So we're going to have the reactants going over and converting over into products. And once that's happened far enough, where enough reactants have formed products, then you create the opportunity for some of the products to react with each other to go back and form reactants. So you're actually going to be seeing both reactions happening at the same time, where the reactants form products and the products form reactants. So let's see that happen. And so in that transfer, we had 10 reactants go to products and 5 products go back to reactants. Now remember, we're separating these with a line just to make it visually easier to see, but realistically this is all mixed in one container. And on paper we write these down as separate things, but remember this is all happening in the same reaction vessel, all happening at once. We just visually like to separate it. And also there's no pausing. I pause this transfer happening, but the transfers are really happening back and forth, back and forth. So let's look at our next transfer. In that case, we had 8 reactants go to products and 6 products go to reactants. And then finally, in this case, we had 7 reactants go to products and 7 products go to reactants. So this is equilibrium. Equilibrium is when you have the rate of the forward reaction, reactants going to products, the one that we're used to, actually be equal to the rate of the backward, the reverse reaction, where the products are going to reactants. The rate in this case is equal going forward and backward, so that means we've reached equilibrium. So that's what the equal in equilibrium means. What the equal in equilibrium does not mean is that the reactants do not necessarily equal the products. It's possible, but most times they do not. So for example, right now we've reached equilibrium, right? If we were to let this keep going, 7 would transfer back and forth forever, essentially. So it would look like nothing happened. But in our final count, we had 13 reactants, and we had 27 products. So because of that, we can kind of see that equilibrium does not mean an equal number of reactants and products. It's a whole separate thing. So a dynamic equilibrium is when the reactants and products are formed at the same rate. So there's no net change in the chemical composition. So we've been looking at the atomic view, but let's say that you zoomed out and you were looking at it with your naked eye. In your reaction vessel, it would look like nothing's happening because the reactants are forming products at the same rate at which the products are going back to reactants. We're showing that here as well, where reactant A plus B They're reacting with each other to form the compound AB at the same rate at which AB is transferring back to form reactants A plus B. And notice that the number of reactants and products is different. So equilibrium is the rate going forward and the rate going back. So like we said, the ratio of reactants and products in equilibrium is not necessarily equal to 1 to 1. It's possible for reactants to equal products, but most times that's not going to be the case. And so let's say there is a way that you can actually produce more reactants or more products if you want to try to manipulate the equilibrium. And that's because of something called Le Chatelier's principle. And that says that an equilibrium can be shifted, meaning pushed more to one side, by changing the reaction conditions, especially the concentration and the temperature. And the pressure is also usually cited as something else you can change. So what we're saying is, in that last equilibrium we looked at, that's going to stick with the same number of reactants and products forever because the rate of change is the same going backward and forward. But there is a way that we can manipulate it so that we can actually shift it to make more products or more reactants. So let's take a look at how that works. So remember before we were at equilibrium, we stopped at 13 reactants and 27 products. Now we're going to add a stress to this equilibrium and see what effect that has. So the stress we're going to have is instead of 13 reactants, we're going to have a total of 24. So we're going to need our 11 particles. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And so we're going to say that we're starting at 24 and we're ending at, we're starting at 27 for the products. And let's see where we end. So we're going to let this reestablish equilibrium. We added a stress to it, so right now it's not at equilibrium. And we see not at equilibrium yet, right? And now you know when we have reached equilibrium, you know what that looks like. And the transfers continue. Still not there. And now we're at equilibrium, right? So you should know now what that means to be at equilibrium. And let's see where we finish off. So we ended with 17. We ended with 34. So 17 of the reactants, 34 of the products. Let's do our comparison. When we first established equilibrium, we had 13 reactants and 27 products. After we added a stress to the reactant side, to the overall reaction vessel, and we allowed equilibrium to be reestablished, there was a change. So we added to the reactants to start this, and over the course of the equilibrium, we went from 24 reactants to 17 reactants, and we went from 27 products to 34 products. So did this reaction shift more toward the products or the reactants? We can see it shifted toward the products, right? So what happened was that equilibrium will shift to the opposite side that particles were added to, or in other words, the opposite side of increased concentration. So we added to the left side, so the equilibrium shifted to the right side. And what that means is, as a result, overall, we made more products over the course of reestablishing equilibrium. This is a way to force a reversible reaction to produce more of a desired outcome, reactants or products. So whichever one you desire for your company, your corporation that you're trying to make a certain product or whatever, you can manipulate to make this happen. And what we're saying is, because we added reactants to the left side, the equilibrium shifted to the right. Equilibrium will always shift to the opposite side that you add to, essentially. And we were able to make more products because of it. So let's look at kind of a visual to help us quickly be able to do this on paper. So right now we're at, quote, equilibrium. Now this is misleading because it makes it look like the reactants, right, A and B, are equal to the products, C and D. We know that that's not true in equilibrium, but this is just a visual tool. So our first simulation will be if we add to the left side, which is what we just did. So we add to the left side reactants A and B. And you know that your seesaw is going to be shifted downward because of that, right? Now, the answer to this, so the question is what happens if you add reactants A and B? The answer is not this original drop on the seesaw. The answer is the change that happens as a result of that. So the answer is that what the equilibrium does to fix itself. So to fix itself, it's actually going to shift to the right. So the answer to this one, what happens when you add more A and B? The equilibrium must shift to the right, which is the product side, because the stress on the system of the particle is added to the left. So the equilibrium shifted to the right in order to correct the seesaw, in order to make things equal out again. So then what happens if we add more products, more C and D? Well, as you can imagine, the seesaw will at first be tilted, But the correction, the answer, is that the equilibrium will have to shift to the left in order to correct the seesaw, because of the stress that we added to the right. So remember, equilibrium shifts to the opposite side of the side that you added to. Which, by the way, when we say added to, sometimes students ask, what do you mean we added to that side? In this case, we are saying that we added to the right side because C and D already exist on the right side. So if we're adding C and D, on paper we have them as existing only on the right side, so that means that we must be adding to the right side. And when we added A and B before, we were adding to the left side, because that's where they already belong. So you add it to whatever side it already exists on. So in this case, we added it to the right side because it was already there. And our final answer was that the equilibrium shifted left in order to correct the seesaw. Alright, so a little bit of a different one. Let's say what happens if we remove reactants. So we're removing A and B, and because A and B exist on the left side, we're removing them from the left side. That means that the seesaw, as you can imagine, would go like this, and the correction, according to Le Chatelier's principle, is that the equilibrium will shift to the left in order to fix that. So again, it's trying to fix itself. And if we remove the product, so in this case C and D, we know the seesaw would temporarily go like this, but in order to correct itself, it would shift to the right, is what we say. So we would shift to the products in order to correct the equilibrium, essentially. Now, that's one way people visualize it. I personally visualize it a very different way that I'm about to show you. You could use whatever way works for you. In this one, we're saying what happens if we add reactants. What happens if we add A and B? And because A and B are on the left side, we have to add to the left side. These are the ones I'm adding, and this is my sort of simulated already equilibrium. So if I'm adding A and B, that means I'm adding in from the left, right? So if I add those in, it's going to push things to the side, forcing equilibrium to shift to the right. And the same thing would happen if we added C and D. It would push things from the right, and it would push it over toward the left, causing more A and B to form. So if we're adding reactants, that's going to push things over and shift to the right. So if you add to the left, things shift to the right. What about if you're removing things? So let's say we're removing reactants from the left. So I'm removing A and B. So if I remove those, I just pretend there's like a big string that these are all attached to, and if I remove these from the left, I'm pulling to the left, which means the products also go to the left. So that's how I sort of visualize that as a result of this equilibrium change. So let's look at our summary. Whatever side is added to, the equilibrium will shift to that opposite side. So if we add to the left, if we add A or B, that means the equilibrium will have to shift to the right. If we were to add C, or if we were to add D, the equilibrium would have to shift to the left in order to accommodate that. Whatever side is removed from, equilibrium shifts to that same side. So if we remove A or B, equilibrium will shift toward that left side. And if we remove C or D, equilibrium will shift toward the right side. So that's it for equilibrium and Le Chatelier's principle. Thanks for watching, and remember, chemistry is everywhere.